Okay, hello class. Today I would like to teach you on how to draw a impulse response filter. Okay, this is the differentials of equation impulse IIR filter that will appear in this form. So this is our transfer function. So from this form, we know that yn is our present output. Okay, present input xn d naught. Okay, our past input where our n is -1, -2, -3, -4 until -m. Okay, we have the past output also. Here is y. Okay, our output. So n -1, -2, -3, -4 until -n is our past output. Past. Okay, because it's present in the present output, it depends on the past sample of the output, okay, past output, and the system we call as a recursive system. Okay, normally we will draw a IIR filter in using direct form 1. Okay, this is direct form 1 where they will share a plus summation here. They are sharing the summation. Okay, so this is how we draw. Okay, B naught. Okay, xn. So when you have b1, so you will have b1 here. Can n minus 1 indicate your delay functions z minus 1. Okay, when you're b2 and you hear b2, z minus 1, z minus 2. So you multiply with your b2, add up. Okay, so you have positive add up. Then we go here, minus 1. So here we don't have, so we don't need to draw anything, and we just draw a straight line. Then go down. Z minus 1 is your here y, z, n minus 1, your delay, and multiply with your a1 minus. So backward, minus a1, so you backward, sum up, and minus a2, so you go down again, a2. So now your delay is minus 2. So we have z minus 1, z minus 2. So you add up, you get your direct form 1. And same for direct form 2. Just you here we just switch the left hand side to the right hand side. Okay, we will get the direct form 2. And we also have the cascade form. Okay, this is the cascade form where we have the 2 denominator and 2 numerator. So it will same like if you divide into 2, z1 your transfer function for your h1 and transfer function for the second one, h2n. So here is your h1 and the h2n. So how we draw this one? First, we have this equation, and then we separate it into two functions. Okay, so this is the first numerator and the second numerator, and this one will follow on the first and multiply 1, we'll get back 1 plus 2 z minus 1. So here we'll draw the first one. So first one is 1 plus z, 3 z minus 1. So 1 came off plus with z minus 1, okay, multiply with our 3, so plus up. So we get this one 1 plus 3 z minus 1. And then from here you go through, we have 1. So we plus with, okay, go down the z minus 1, multiply with 2. Okay, we go up with plus. So this one is the first transfer function. Then multiply with the second transfer function, we just go straight, multiply. So here plus, okay, first one, 1. Okay, you can go straight line 1 plus with z minus 1 multiply with 1. Okay, plus up. So because here is 1, so here is 1 line. Straight away, 1 line. Then we get our output yn. So this one output input xn. Okay. So today we will go for how to draw a IIR filter. Okay, by using Matlab. Okay, how to design. Okay, so first we are using the first one. This one is the function from the Matlab. This function is to calculate the minimum order of our digital or analog Butterworth filter. So we see BUTT. BUTT means Butterworth order. ORD means order. Okay, the required by the frequency our filter design specification. So we have N and WN. Okay, N which means our order. WN is our omega. This one WP is uh, mm, our W is uh, our frequency for our passband. WS is frequency for our stop band, and RP is our ripple for passband and ripple for stop band. So here are the other Butterworth filter. This one is for Chebyshev. type-1 order, same for WN, WP, WS, RP, RS, same. So Chebyshev second order, so Chebyshev CHB 2 order, second order. Okay, and Butterworth, okay, this is to design Butterworth, BETER. So to design a low pass, high pass, band pass, or band stop for the Butterworth filter. So here we can set it by our F start. So F start here we can set it whether it's low pass, high pass, band pass, or band stop. Okay, for Chebyshev type-1. So we also can B and A is our transfer function. Okay, transfer function B is numerator and numerator, and N is our Chebyshev order. Okay, our filter order, and ripple for passband, frequency for passband, and this one is our frequency type. Frequency type you can set it at either it's lower, low pass, high pass, band pass, or band stop. Okay, same for here also. This one is the other function for Chebyshev too. And okay, so that's all for the IIR filter. So now we will go to how to plot a IIR filter. Okay, so we have Matlab here. First, we have close all, clear all, and CLC, which means close all the windows for the few for the window, everything, the figures, etc. Clear all, which means we clear our workspace and also our everything workspace. And CLC is clear our command window. Okay, then you can try here. Okay, so when we are trying, so you know that here is cleaning and everything is cleaned up. Okay, then this one format long. Format long is where we set the output format to be the long fixed of decimal format. Because later on we will calculate with pi, so pi will giving the very fixed long fixed decimal format, and we display the pi value. Okay, so we are using the format long. Then this one is RP, band pass ripple. RS is stop pass ripple. WP is our pass band frequency. W S is our stop band frequency, and FS is sampling frequency. Okay, then we have W1 is our frequency equals to 2 times our band pass frequency divided by FS. Okay, this one you can know that when we doing the calculation for our frequency, when we doing our calculation for our frequency, we will calculate this one. So to normalize the band pass angular, so we will have WB equals to 2 pi FP divided by FP. So in order to get our WP, we will have W divided by this one, we will get 0.2. Okay, this is how to calculate our angular frequency. So same for this one. So same for our stop band H angular frequency. So this is what we do for these two formula for our passband and our stop band to do these two calculations. Then we will have our Butterworth order. N is the order, Wn is our omega. Okay, so W1 is the angular frequency calculate for the stop our band pass. Okay, this one is our angular frequency for our band pass band. Okay, then we also have the angular frequency for our stop band. Okay, then these two value enter here, Rp, so we take the stop ripple, and Rs, the band pass ripple. Then S. Okay, to know what is this S, we can go to the Matlab help. Okay, by typing this thing, this Butterworth order. Okay, we can see here. So we can just go to the toolbox and we can know what is the S mean. Okay, here is the have the. So if you don't know what is this, here have the explanation. So see, this is our function that we provide by Matlab. So here have indicate explanation what is WP, WS, RP, and RS. So you just refer here. So for your information, RP and RS should be in decibel. Okay, to be in decibel. Okay, so this is the filter type, low pass, okay, high pass, Butterworth, band pass, or band stop. So you can refer here. Okay, so this is the how it calculates and how are you doing. So the S indicate here is okay. Whether have the S or not. Okay, this one is our S. So we can see what is this S meaning. Okay, this S is for the analog domain. So when you are calculating in analog domain, you need to put the S inside. If you are calculating in the digital domain, okay, you don't need to put the S inside. So we can refer here. Refer here to find the minimum order for the cutoff frequency of the analog filter. So you specify the frequency of WP, WS, okay, described in the band pass, the description of the stop band and the band pass filter parameter. Okay, from here is so the frequency is to be radian per second, and the band pass or the stop band, the pass band or the stop band can be infinity. Okay. So next, we have to understand what is butter. Okay, so you also can go to help, find what is butter. Butter means which means Butterworth filter design. Okay, you just can find what is butter. So from here, this is what is butter. So butter, which means is Butterworth filter design. Okay, so we can see to return the transfer function coefficient to an n order of our low pass frequency and low pass digital Butterworth filter with the normalized cutoff frequency Wn. So Wn here is our cutoff frequency. Okay. For example, if you want to change your type, if you didn't mention here, so your type will be a low pass. If you mention this as type, so you're putting something inside here. So how you putting inside? You can putting high pass, band pass, or band stop. Okay, example. We can go to example. Okay, this one is the example for stop band. So band stop Butterworth filter, you just put the semicolon, the column here, stop. Okay, you will get a band pass filter. Okay, clear? So anything that you don't understand, you may refer Matlab help. So ZPK, what's the meaning of ZPK? Okay, ZPK is to design a low pass or high pass or band pass for the band stop digital Butterworth filter. Return it to 0. Z represent 0, P represent your pole, K gain. So the syntax can be included into the argument of the previous syntax. Okay, clear? So if you don't know, you can click inside. Okay, have a look. What is this one? Zero pole and gain. So this is a zero pole of gain filter. So which means we as the two column vector of n. Okay, which means we are return it into this form. For the digital filter, our transfer function will be in 0, pole, and k. Okay, so it is the k, which means is a scala. Okay, here. So your transfer function will be represented like this. So for analog, your transfer function will be represented like this. Okay, in this form. Okay, clear? So this is why we are using ZPK Butterworth and WN. Okay, so next, we are convert our zero pole gain filter parameter to a transfer function form. So we are using ZP to transfer function, zero and pole to transfer function. So we can here. So for information, you can just find here. Okay, this is to convert the zero and gain parameters to the transfer function. So okay, this is the format. Find a rational transfer function. So from just now that form, now we are convert it to B and A. We want to find the rational of our transfer function. So we want to find it in this format, our transfer function format. Okay. So this is our A, B, and A value. Okay. This is our pole value P, and we have the value of the K and the Z. Okay. So is it clear? So then, okay, we use this one is display it again, okay, into a Butterworth transfer function. Okay. Then this one omega, we are plotting our graph from 0 until okay pi. So the interval is 0.01. So H, okay, H ohms. So this one we can find. We are plotting our transfer function into the frequency, okay, into a frequency. So this one is a normalized frequency. So B and A, so the value will be in radian. So this one is our omega. Okay. Okay. So H is our frequency response. Okay. Then, okay. Then we have this M equals to 20 log absolute of H. Okay. Absolute is magnitude lah. So we are counting this frequency into 20 log of this magnitude H. Then AN is our angular phase in radian. Okay, so we are plotting in figure 1. So you can try here now. We select it and right click, evaluate. Okay, so now you have to enter. They will ask, first question they will ask, what is your refer? So by referring the questions, now we go to the question. Okay, this is the question. Okay, determine the lowest order of this RRI low pass filter for Butterworth, Chebyshev, and type-1 and type-2. So now we are doing for Butterworth. So referring here, okay. So this question given, the pass band ripple is 0.5. So we are enter 0.5. Then our stop band attenuation is 40 dB. Remember, these two value is in dB. So you must ensure that the question is in dB and you just only can enter. Okay, next. Okay, this one pass band frequency. Okay, your frequency is 4. Sorry. Okay, your frequency is 4 Okay, 4,000 hertz, then 8,000 hertz. Sampling rate is 40,000. Okay, enter. Then your graph will be plotted. So this is the graph for the gain in dB. So this one is your normalizer frequency. Okay, this one is your phase in radian and your normalizer in frequency. Okay, I would like to teach you how to plot this graph in if in degree. So for example, you want to plot this graph in degree, you can just select this one, copy, and just put in the command window. Okay, paste, enter. So you will get another graph here. So this is the magnitude, same also in dB. Okay, same also in dB, and the phase in degree. Okay, clear. So this is the phase in degree. So this is the same graph with the previous one. Remember, it's radian per sample. It's a normalized frequency. Okay, now we go to the next one. Okay. Now this question asking, what is the lowest order of the IIR filter? So just now we know that this transfer function and here and this line of the equation and here is represent our filter order. So we can just and enter. So we know that our filter order is 9. Okay. So for your information, you also can refer your value from here. So we can find our value n is 9. So double click on workspace, we can find out here. Okay, in order to know your transfer function b and a, okay, this is our transfer function, okay, b, and this is our transfer function of a. So we can find b is equal and a is equal. So we have the transfer function value. Okay, this is our transfer function of the denominator and numerator. Okay, so there is a lot of the value that you key in just now. This is the value that you key in. Okay, you want to know whether how much is our cutoff frequency. So cutoff frequency is Wn. This equals 0.23979 blah blah blah. Okay, Wn is our, so we can refer here. When you double click here, you can get your value here. Okay, so just now I say long format, that's why you can see the long format here. Okay, so you can refer all the value from here. Okay, thank you. This is how we plot Butterworth filter. So for your information, if we want to plot a Chebyshev filter, you just have to change this to Chebyshev order and change this to be Chebyshev. If you want to plot Chebyshev order 1, you just change this and this in order for you to get the Chebyshev. Okay, thank you. Okay, now we continue for Chebyshev type-1 filter. So same for the Butterworth filter coding. You just have to enter the RP, RS, WP, WS, frequency, sampling, and then angular frequency for our band pass and the angular frequency for our band stop band. Then now here you focus here. Wn is the end order. Wn is the cutoff frequency. Chebyshev 1 order. Okay, W1 is our angular frequency for pass band. W2 is the angular frequency for stop band. Okay, RP ripple frequency and RS ripple for the stop band frequency. Okay, stop band. Then RP is our ripple from band pass. Okay, RS is our stop band for our ripple. Okay, then you have a BA transfer functions, denominator and numerator equals to Chebyshev 1. Okay, N is the N order, R3 and your WN. Okay, now same for here, you have the angular, your omega. So we plot from 0 until 5. So this is the same. Okay, then we just execute. So now we execute. Okay, when you execute, so based on the questions, you have to enter 0.5, your band ripple. Okay, your stop band is 40. Okay, stop band ripple, pass band here, 4K, 4,000, 8,000, and then 40,000. So done your graph. So you can find your N is how much? Your order is 5. Then you know your WN, your cut-off frequency is 0.2. Okay, so that's all. Okay, then you can change for Chebyshev for the second order. Okay, Chebyshev for second order. How you want to do it? You just have to change it to be second order. So we just have to change the Chebyshev to order and Chebyshev to here. Okay, so now you have to be careful when Chebyshev second order, this one will become RS. So for this, for your understanding, if you don't know, you can refer the Matlab help also. Okay, now we go. Here we go. So we just run it for second order. Okay, just execute. Now you key in 0.5. Okay, 40 dB, 4,000, 8,000, 40,000. Okay, this is the graph. Then we have our N order, and also we have our cut-off frequency. Okay, WN. Okay, 0.2. Okay, done for Chebyshev step 1 and Chebyshev step 2. Thank you. Bye. So remember to subscribe my channel and click on the bell for notification. Bye.